These are the frequently asked questions for Algebra 2 for Section 8.3, Day 2. I'm going to start with number 23. And number 23, what they want us to do is find the horizontal asymptote of the graph of each rational function. So we have y equals 5 over x plus 6. And remember that the horizontal asymptotes are all about the degree of the polynomials that we are dividing. So the degree of the polynomial 5 is a degree 0 polynomial, because what really we have up there with our x value for the variable is x to the 0 power. And then our denominator here is a 1. And when the degree of the numerator is less than the degree of the denominator, then our horizontal asymptote is the line y equals 0. So that's what we see in number 23. Again, I'm talking you through these a little bit slow because I want to make sure that you're catching every little piece that we go through there. Hopefully, after you do a few of these, you'll realize, oh, look at that, there's no 0 on the top, it's x to the first on the bottom, so it's y equals 0, and just make those connections immediately. Then number 26, we have y equals x squared plus 2 over 2x squared minus 1. So the degree of the numerator is a 2, and the degree of the denominator is a 2. And when the degree of the numerator matches the degree of the denominator, you use those leading terms. In fact, you use the leading coefficients of the leading terms. So that would mean I need a coefficient in front of that x squared, because this is the fraction that I'm going to use for my horizontal asymptote. So the horizontal asymptote here will be y equals 1/2. And then the example that they didn't have up here is when the degree of the numerator is greater than the degree of the denominator. And the reason they didn't put that one up there is because you don't get a horizontal asymptote when that happens. 29, 30, and 34 give us three each really unique examples of what happens when we are graphing our rational functions. So for 29, first thing we do is think about factoring that. That'll be x plus 2 and x minus 2 for our numerator. And in the denominator, we can take a 3 out. And again, that's the first thing you always want to check is there a common monomial factor that you can pull out of each one of these. So now I would start by going through what are my asymptotes, what are my points of discontinuity, all of those types of things. So as we've talked about in class, our domain, the restriction comes from the denominator. We cannot divide by 0. So in this case, if we were to use a 2, then that would happen. So we can't use 2. That's outside of our domain. That is a point of discontinuity. So that point of discontinuity is x equals 2. And then we have to figure out, is that removable or is it non-removable? And we see that yes, x minus 2 is something that we could cancel out. Remember, canceling is a form of division, and when you look at this, you can see we are multiplying here, so we can cancel those two pieces out because they match each other perfectly, and we see that multiplication. So that is a removable discontinuity. What that means to me as I graph this is that I'm going to have to leave a hole where the x value would be 2 for this graph. Then we look and see whether or not we have any vertical asymptotes. Well, if we cancel that out, there is nothing left in the denominator to give us a vertical asymptote, but there might be a horizontal asymptote. So let's go back up and take a look at the original again and look at those degrees. So the degree of the top is greater than the degree of the denominator. This one is a degree 2, and this one is a degree 1. So no, we don't get a horizontal asymptote. And last but not least, we might want to go ahead and find the x-intercepts and the y-intercepts. That often gives us a good look ahead at what we should prepare for. So x-intercept is when our y value is going to equal 0, and that happens when the numerator is 0. So if we put a negative 2 into this set of parentheses, we will have an x-intercept. Now notice we have already canceled out that x minus 2, and that means that's not in our domain. So you might be thinking, hey, I should put negative 2, 0, and 2, 0 down, but Remember, 2 is not in the domain of this function. It does not exist there. And then the other thing that we need to do for the y-intercept is we need to take a 0, put it in for x, and then see what we would get. So if we put a 0 into both of those x positions, it'll be 0 minus 4, which is negative 4, over 0 minus 6, which is negative 6, and that reduces to 2/3. So our y-intercept is 0 2/3. So let's see what we know so far. We know that at x equals 2, we're going to have something that's removable. But we don't have any vertical asymptotes. We don't have any horizontal asymptotes. We know that the graph is going to cross the x-axis at negative 2, 0. And it's also going to cross at 0 2/3. Oops, too high there. Like so. That's all we know. But remember now that when we have these more involved graphs, when we're not doing y equals a over x minus h plus k, that what we're going to do is we're going to grab a graphing calculator and we're going to punch this in and we're going to use our table feature to get some points. So first things first, I better slide this up so we can see the original function. And then we go to our y equals. And we're going to have to be careful that we are using parentheses. I mean, absolutely, we have more than one term in our numerator and in our denominator. So we'll need parentheses and then x squared minus 4. Parentheses divided by parentheses 3x minus 6. And then I'll just hit zoom 6 because the graph that I had up there was a negative 10 to 10 graph. And it appears to be a straight line because that's what the calculator knows to do. It doesn't know that it should leave a hole when x equals 2. So what we would do is we would hit second table and we would write down some of the numbers that we see. And at this point you see, oh, yep, there it is. There's my negative 2, 0 for my intercept. And at 2, I see that there's an error. And that tells us we were right to put in that point that we aren't going to be able to use from our domain, which is x equals 2. And then you would just go ahead and grab some of these values and graph those. Let's see if I can do this on the 2 screens at one time. I think I can pull it off if I move this up a bit. All right. So at negative 4, we are at negative 2/3. And I have already the couple of points that I found with the x and y intercept. And then at 1, we have 1. 2, again, we have to leave a hole in there, so let's go with 4, 2. And again, this appears to be a straight line, but we know right there we have to put a hole in our graph. And line that up with a hole. Again, I want to make sure that it is obvious. That we have a hole in that position because we know that that is a point of discontinuity and it is a removable one, which means it's a hole. So that's the first type. There's actually 3 types of graphs that we are going to see as you do this homework. So let me clear this off and let's get to another style of graph. And that will be number 30. So we go after this the same way. we look at our numerator and realize there is no factoring that we can do with that. But our denominator, we definitely can pull an x out of both of those terms. And when we do that, we notice we have a difference of 2 squares pattern down there. So we'll be able to factor again. Now, this is really important for us to see our points of discontinuity. So right now, our domain is all reals except x can't be 0. If x is 0, then that little point right there is going to be a problem because it'll make that whole denominator 0. X cannot be -2. I should really put the word and in here. And x cannot be 2. So we have quite a few numbers for our points of discontinuity this time. We're looking at 3 of them. X equals 0, x equals -2, and x equals 2 for our points of discontinuity. And we notice one of them is going to cancel. The x value that's there all by itself, that's the one that would cancel out. So I'm not going to totally scratch it off, but what I want to do is change colors there so that I can see when I come back to work on this later that we cannot put 0 into this function. So we have one removable, so x equals 0, removable, and then x equals -2 and x equals 2 are non-removable. And that means they are vertical asymptotes. So there are some vertical asymptotes for us. And then we can go ahead and think about horizontal asymptotes by going back up and looking at degree. Well, the degree of our numerator, that's an x to the first, so that's a degree 1. And our denominator is a 3. And when the degree of the numerator is less than the degree of the denominator, then we get the horizontal asymptote y equals 0. All right, other things we could go ahead and do. X-intercept, figure out when our numerator would be 0. And we look up here and we realize, we already said x can't be 0. The 0 for 4x would be 0, so none. We don't get one. Our y-intercept, let's see what happens if we plop a 0 into that original function up here. 4 times 0 would be 0, and then if we put a 0 into the denominator, we're undefined. So once again, we see this one doesn't exist. And what does that mean? That means this graph is not going to cross the x or y axis, at least at different parts of the graph. Hyperbolas, different things happen sometimes based on how many sections of graph that you have. And in this one, we want to remember that we have vertical asymptotes at 2 and -2. And we have a horizontal asymptote at 0. All right, now what I need to do is grab a calculator because remember, I can't put any points on this one. My x and y intercepts were both undefined. So I have to grab the calculator and let's go back and take out the graph we were looking at earlier. And again, make sure you use parentheses for the numerator, which is our 4x, and then divide, and then parentheses for your denominator. X to the third minus 4x. You can either hit graph or zoom standard depending on what you have there. Now, what we'll notice is it appears that we are going to cross that horizontal asymptote. Well, we do in 2 of the 3 sections, but it is an asymptote for the middle section. So that's why we have possibilities here that didn't exist with y equals a over x minus h plus k. These graphs are very complicated, and so an asymptote will work for a portion of the graph but not necessarily the entire graph. So again, what we would do is we would hit second table, and we would get some points that we can graph so that we can see what we have. So at -5, we're at, about 0.2. But as we go further and further along, we see, in fact, even though the graph looked like it was crossing, it isn't. So again, we can't trust the graphing calculator for everything. We have to use our head for some of this. So -5, about a 0.2. Just above, and -4, 1/3. And then use that as your guide because we know what's going to happen. And then we have to take a look at what's going on between -2 and 2. There we go. I knew this was going to be an issue. My smartboard has not been working well when I have the calculator on. There we go. So at -2 we see our error, and then at -1 we have -1 1/3. And then we see at 1 we have -1 1/3. And we will graph that from what we saw on the main screen. Then back to the calculator to see some positive values here. And this one was very, very close to the line y equals 0, but we see the same kind of thing. So at 4 we have 1/3, and at 5 we have 0.2. And again, we saw from the visual of the graph earlier, from the entire graph, that it's going to approach, but never quite going to touch. And that's a pretty good simulation of what we see from the graph. So that's the second type of graph. Pieces that we get, other pieces that are missing. And then I wanted to do number 34, so you have an example of the last type of graph that we can see in this assignment. And the smartboard locked up. Number 34 is already in factored form. So we'll go through this one again, thinking about the domain restrictions. Domain, again, the numbers that we cannot put in the denominator because they'll make us divide by 0, and that would be a -2 in this one. So x cannot equal a -2. So points of discontinuity, x equals -2. And we cannot cancel that with anything in the numerator, so that is a non-removable point of discontinuity. So what does that mean? It means that is a vertical asymptote at x equals -2. Horizontal asymptote. Well, the degree of the numerator is a 1. The degree of the denominator, if we multiplied all of this out, would be a 2, because x plus 2 times x plus 2 will give us a perfect square trinomial. So the degree of the numerator is less than the degree of the denominator, which gives us a horizontal asymptote of y equals 0. Now, other pieces, let's check for an x-intercept and a y-intercept and see if we can get those. So with the x-intercept, we need to get y to be a 0. The only way that's going to happen is if 3x equals 0, and obviously that means at 0. So we're going to get 0, 0 if we're looking for x-intercepts. Y-intercept, we have to put a 0 into the function and see what we get. Well, if we put a 0 in, we'll get a 0 on the top, and it really doesn't matter what we'll get on the bottom because it's going to be 0. So our x-intercept really is also our y-intercept, and that's at 0, 0. So far we know that is absolutely a point on this graph right there. We also know that we have a vertical asymptote at x equals -2. And our horizontal asymptote at y equals 0. Which kind of drives us nuts because we see, hey, there's a point over there at 0, 0 that's on that asymptote. And again, doesn't necessarily mean that that's an asymptote. The horizontal asymptote is for the entire graph. It means for that portion of the graph, which would be, in this case, anything to the left of x equals -2. And now I need to get this so that we can see it. Or probably not going to be able to make that happen, so I'll just punch it in over here so that you can see it. All right, so with this graph we had a 3x in our denominator. In our numerator, 3x, and then in parentheses, divided by, and then we have x plus 2, the quantity squared. All right, let's get a quick look at that one. And we can see, yes, the x-axis is an asymptote for the left portion of this graph, but it's not for the right portion of this graph. So now, second table, and we'll get some points. But I need points that are going to be around my -10 to 10. So let's see some negatives and then we'll come back and get some positives. Alright, so we do see our asymptote at x equals -2. It says that that is an error. So let's get a few points graphed. And it continues to go negative. All right, lots of stops and starts here trying to get my graphing calculator to cooperate. So we take a look up there and we'll just get some of the points that we need for this graph. And we have -4, -3. And -5, -1 2/3, which gives us a pretty good look at the left-hand portion of this graph. And then on the right-hand portion, we have 1, 1/3. And I think I'll go over there to probably 4, 1/3. So again, that portion of the graph not necessarily adhering to our horizontal asymptote for that portion. All right, now I'm really tempted to close off the graphing calculator because it might mess up, but we need it yet. Number 35 says how many milliliters of the 0.5% solution must be added to the 2% solution to get a 0.65% solution, and use the rational function given in problem 5. So that was 100 times 0.02 plus x times 0.005 all over 100 plus x. So we see what's going on here is that they have 100 milliliters of the 2% solution. And they are going to add some amount of the 0.5% solution. And they're starting with 100 milliliters, but they have to add, remember, they're going to add that 0.5% solution. Now, we want that to come out to be 0.65%, which would be 0.0065. So what we're going to have to do is y sub 1 and y sub 2 this. What you might want to do, the pretty obvious thing to make it punch in a little bit nicer, is do 100 times 0.02. That's going to give you 2. And we normally like to have the x behind. So that might make this a little easier to punch in. So let me try this with the graphing calculator and see if it behaves itself. All right, so y equals, and we have our parentheses, 2 plus 0.005x divided by, after you finish your parentheses there, parentheses x plus 100. And we need to know when this is 0.0065% solution. Because remember, it's 0.65%, which means we have to put a couple zeros in front of it. So now that's going to change our window a lot. For instance, x is standing for how many milliliters? Remember, milliliters are really, really small. So it's possible it might even take more than 500 milliliters. Let me go with 1,000. When you work in the pharmacy, the bags come generally in 100 milliliters, 500 milliliters, or 1,000 milliliters. So let's go ahead and try it with 1,000. And then we want a very, very small number. So we're going to go from 0 to, and I think I'm going to go by that 0.01, so 1/10. And I will have it graph this in thousandths for a scale. And we'll see what happens there, if we can see that intersection. So there's the graph of what's happening to the solution. And it's a good thing that I put 1,000 in there, because we can see as this is getting to the right portion of the graph is where the intersection is. So second trace, number 5, get Blinky in there. And again, I'd like Blinky to have an easier time of it. But especially with the graphing calculator on the screen here, I think I'm just going to call it right there. Enter, enter, enter. And that tells us that we need, kind of hard to read there, but we need 900 milliliters. A little easier to see over here at this portion, that it's going to be 900 milliliters that we need to add. So for number 35, our answer is 900 milliliters. All right, next up. Okay, thought I was going to have a freeze-up problem again here. Find the vertical and horizontal asymptotes, if any, of the graph of each rational function. So I take a look at the screen that they have in 36, and I'm thinking to myself, there's a vertical asymptote there, and another one right there. So then it's just a matter of counting the little notches, and that's going to be 3 and -3. So vertical asymptotes at x equals 3 and x equals -3. And then, absolutely, y equals 0 is an asymptote for the 2 branches. Not for the middle portion of this, but for the 2 branches. So that is going to be a horizontal asymptote at y equals 0. Then, number 38, there isn't going to be a vertical asymptote. There are no breaks in this graph where I could say it looks like there should be a vertical asymptote. But notice how it's symmetric across the x-axis there. So that's an indicator that we would have a horizontal asymptote of y equals 0 for that problem. Number 39, this one says we have a basketball player and they've made 21 of their last 30 free throws. So far, 21 out of 30. And that's a percentage of 70%. If you take 21 and you divide it by 30, you get 0.7. How many more consecutive free throws does she need to raise her free throw percentage to 75%? Well, we don't know. We don't know how many she's going to try and shoot. We don't know how many of those she's going to make, but it said they have to be consecutive free throws, so that means she has to make them. But if we're going to add those to the numerator, we also have to add those to the denominator because her total is going to increase as the number of shots that she makes increases. And now what we want that to do is we want that to come out to 75%, which would be 0.75. So we could do this one by hand, and quite frankly, I think that's what I'm going to do because I'm tired of the way that the calculator is behaving on the smartboard. We can slap a 1 down here, and then we can go ahead and cross multiply. So 0.75 times 30 plus x equals 21 plus x. And then we could just take 3/4 basically of 30, and that's 22.5 plus 0.75x. And then we could subtract 0.75x from both sides. And now it's just like working with money. If we have $1 and we subtract 75 cents, we're going to have a quarter. So over here we now have 22.5, and over here we have 21 plus 0.25x. That's really hard to read. So next up would be to subtract 21 from both sides. And then we would go ahead and divide. So at this point you say, okay, $1.50. How many quarters in $1.50? And that's going to be 6. So it would take 6 shots. And again, she has to make all of them right in a row in order for her to reach her goal on that one. All right, what is next here? I think I have another word problem. A student earns an 82% on her first test. How many consecutive 100% test scores does she need to bring her average up to 95%? All right, so easiest way I think to do this one is just to say, you know what, I know 82% is 0.82 rather than thinking of it as 82/100ths. And she's going to have to add some test scores. Now the thing is, we'd want to know the percentage on those test scores, and we do. That's 1. So it's really plus 1x. And then, because we don't know the total, we could say, well, she took 100% of the test so far, and we're going to continue to add to that whatever our 1x comes out to be. And like I said, you could use this as 82 over 100 as well, but you can see you'd get exactly the same thing from the front portion of this fraction. And what we want is for that to come out to be 95%. So again, rather than trying to graph it on the graphing calculator as y sub 1 and y sub 2, I'm going to cross multiply, so 0.995 times x plus 1, or 1 plus x, it doesn't make any difference, equals x plus 0.82. So 0.95x plus 0.95 when we distribute the 0.95 through the parentheses. And then we would go ahead and move our x values over, so subtract 95 cents x. 0.95 equals, well, $1 minus 95 cents would be a nickel. And then we'd subtract the 0.82. And then divide both sides by 0.05. And that should give us our answer, which would be 2.6. But you can't take 2.6 tests, so she would have to take 3 tests in order to make the average that she wanted to make, which was 95%. And again, you could do the y sub 1, y sub 2 on the calculator, you're still going to get the 2.6. Next problem up, error analysis. A student listed the asymptotes of the function as shown at the right. Now I'm not even going to look at their answer because remember it's wrong, and sometimes by looking at a wrong answer we convince ourselves that it's right. So what I need to do is I need to factor, and I don't see a common monomial factor. Also don't see perfect squares, so I just need to find 2 numbers that multiply to positive 2 and add to negative 3, and that's negative 2 and negative 1. And then in my denominator, again, there is no common monomial factor. As we look at this, we see that this is not a perfect square because we have the plus 5 in the back. So now what we want is 2 numbers that multiply to 5 and add to 6. So multiplying to 5 would be 5 and 1. Now, as we look at this, we realize there's nothing that's going to cancel out here, so there's not a hole in this graph, but our vertical asymptotes come from the zeros of the denominator, so that's going to be x equals negative 5 and x equals negative 1. And then horizontal asymptotes, well, the degree of the top equals the degree of the bottom, so that means we have to take those leading coefficients as a fraction, and that would be 1 over 1, which is just 1. So y equals 1. Now let's see what they did here. It says vertical asymptotes at 1 and 2. Well, they found the zeros of the numerator. That's not what you're supposed to use. You use the zeros of the denominator. And then it says horizontal asymptotes at negative 1 and negative 5. Well, those are the vertical asymptotes. So what was their error? They used the zeros of the numerator for the vertical asymptotes. They need to use the zeros of the denominator. Then, horizontal asymptotes are found by investigating degree. Not zeros, as they have done. So now we've explained it and we have fixed it. Next one up is to sketch the graph of each rational function. And here's what I'm going to do with these two so I can turn off that graphing calculator because it's messing with my smartboard here. I'm going to go ahead and work you through all of the points that we would want to know about before we put it into the graphing calculator. Alright, now that the graphing calculator is off, hopefully I won't have so much trouble with the smartboard. So here's what we need to do. We need to factor so that we can see what's going on. So I look at my numerator and I realize there is no common monomial factor, but that appears to be a perfect square trinomial. I just need to check my middle term. This is x squared, the last term is 3 squared, and then we need to check If you multiply those two together and multiply them times 2, do you get the middle term? Well, x times 3 is 3x. If you multiply it by 2, you get 6x. So that is a binomial squared, and that binomial is x plus 3. And that brings us to a big aha moment right there. So let's go through this. Domain. X can't be negative 3 because that would give us a 0 in the denominator, and that's undefined. So that is a point of discontinuity. And it is removable because we can see that one of those x plus 3's would cancel out. I'm going to go ahead and write it over here and show that canceling. So it is removable. That means we're going to have a hole at x equals negative 3. Then we would want to go through and try vertical asymptotes. Well, we don't get any. There's nothing else left in the denominator for us to use for a vertical asymptote. But horizontal asymptotes, let's take a look. The degree of the numerator was a 2, and the degree of the denominator was a 1. And when the degree of the numerator is greater than the degree of the denominator, we don't get any of those. So that's out. Then we would try our x-intercepts, which is when y equals 0. So we come up here and take a look and say, all right, well, if we put a negative 3 in here, then we'll have a numerator that's 0. But remember, we can't put a negative 3 in there because we had to leave that out of our domain. No x-intercept. Y-intercept. Well, what happens if we put 0 into our function? 0 plus 0 plus 9 will give us 9, and 0 plus 3 will give us 3. So we do get some information there at 0, 3. And so at this point, like I said, I'm going to leave you guys to go ahead and put this in here. We know there's a hole at x equals negative 3. So what you would want to do is use those double parentheses and then your table feature, but make sure that everything matches up with what we know is supposed to happen with this graph, because the calculator does not know to put holes in the graph. It actually does the opposite. The calculators always try to connect up any pieces that they can and make a continuous graph. So it's only our brains that are going to keep us from getting that wrong. All right. Now, with 45, it is already in factored form, but you're going to notice that I'm going to move that negative up here, just so that we can look at this and realize, you know, the negative is going to be used either in the numerator or the denominator, but not both positions. You always just use it in one. So we'll start with domain, and we can see that a 1 would be a bad number, so that's out. So point of discontinuity, x equals 1. Removable or non-removable? Well, we cannot cancel that x minus 1 factor out anywhere. So this is non-removable, which tells us that that is a vertical asymptote at x equals 1. Then the next thing we would probably do would be to go after our horizontal asymptotes. Well, the degree of our numerator here is a 1 because that's x to the first. And if we were to multiply this binomial out, we would have an x squared. So the degree of the numerator is less than the degree of the denominator, which means we have a horizontal asymptote of y equals 0. Next up would be finding our x and y intercepts. So x-intercept is found by finding a number that would make our numerator 0, because it has to be on the top, remember, we can't have zeros in the denominator. And that would be a 0. If we put a 0 in here, 0 is non-negative, so our x-intercept is 0, 0. And then our y-intercept is when we put a 0 into this, so our y-intercept is going to be 0, 0. So things that we can finally put down on one of these graphs, we know that we have a vertical asymptote right here at x equals 1. We know that we have a horizontal asymptote at y equals 0, and we know that the graph is going to cross at 0, 0. And again, at this point, I would want you to go ahead and plug this into your calculator, put the negative x in parentheses, and then put your x minus 1, the quantity squared, in parentheses. That way the calculator knows exactly what you want from that graph. And that's what we have to do. We have to be smarter than the calculator and tell it what we want. Then number 46 is talking about CDs that are manufactured for 19 cents each. The development cost is $210,000. The first 500 discs are samples and they're not going to sell those. So A says write a function for the average cost of a disc that is not a sample. Well, here's the deal. You've got that $210,000 to make up for. So how are we going to make money off of these? Well, we have this $210,000, and this is average cost. So $210,000 plus, unfortunately, 19 cents a piece. And we have to divide that by the number. Oh, first I better put a piece on here since we don't know how many we're going to make. Divided by how many total we have. Now, unfortunately, it's the total that we're going to make money on. And they said the first 500 of those are just samples. They're not going to sell those. So however many we make, we're going to have to subtract 500 from that in order to find out what that average cost is going to be. So $210,000 plus 19 cents per disc. We don't know how many discs, and we don't know how many discs for the denominator, but we know we have to subtract those first 500 because those are going to be giveaways. They're going to be samples. So we'll put that as A equals Y. And then it says graph the function. I definitely would want you guys to graph something with really huge numbers like this on your graphing calculator so that you can make a sketch. All right, so I turned this off for a minute so that I could try to get a good look at what was going on with this graph. And I think probably the best look that I had was setting my X window from 0 to 10,000 and then my Y from 0 to 5,000. And we can see that the cost really does go down as you are producing more of those. Now B asks what is the average cost if 5,000 discs are produced. And so what we have to do is plug these in and see what we get. So average cost is what our formula was for. What you would need to do for B is to go ahead and put 5,000 in for X into both of those spots, and then 15,000 the second time around. So you're changing your X values for that. And that one comes out to $46.88 if you produce 5,000 discs, and then $14.68, a big difference, if you produce 15,000 discs. And then C is how many discs must be produced to bring the average cost under $10. You could put the 10 in for Y, and you could solve this by cross multiplying. Or you could put in $10 for Y sub 2 and graph it and hope to be able to see it. But if you do that, what you're going to have to do is you're going to have to change your Y values so that you can get a better look at that portion of the graph as you're going through there. So with that one, it will be at least 21,917 discs. So you definitely would have to tweak your window a bit to get that to a point where you could see everything. So let me see if I can get that for you. So if you have your X values from 0 to 30,000, and then you change your Y values to 0 to 20, you will be able to see the intersection of those two. And then D says, what are the vertical and horizontal asymptotes of this graph? All right, well, we've got our 0 down here. That would give us X equals 500. So that's our vertical asymptote. Horizontal asymptote is all about degree. So we have two first degree polynomials, and we would take those leading coefficients, and this one would be a 1. So it would be y equals 0.19, and that would give us our horizontal asymptote for that graph. So, good problem, just tweaking the window a lot in that one to get anything to show up because we have such high numbers. You might notice when you look at the answers in the book, they actually changed this into thousands and went after it that way, so it took some zeros out of this problem. Then number 50 says, what is the x-coordinate of the whole in the graph of y equals x squared minus 9 over 2x squared minus x minus 15? So, we will go ahead and factor the numerator, and then factor the denominator. Now, normally we would sit and say, all right, I've got a 1 and a 2 and 1 in the front, and then, go with all the possibilities in the back for the 15. However, chances are pretty good that we're going to have a 3 in the back of this because they're asking us what is the x-coordinate of the whole in the graph. So, I'm going to take a chance and say that it's going to be x minus 3 and see whether or not this works out. So this would need to be 2x because these two positions have to multiply to 2x squared, and then this would have to be a plus 5. And then I'll just check that real quick with FOIL and see if it works. First times first, outside times outside, inside times inside, last times last. So kind of an educated cheat on finding something that's going to work here. So we see that x minus 3 would cancel out. That makes it removable. So the x-coordinate would be 3 in this case. Then number 52 says, what is the y-coordinate of the vertex of this parabola? You have to remember our form, which was y equals a times the quantity x minus h squared plus k. And the vertex is hk. So then k, our 5, is going to be the y-coordinate. So 5 is the y-coordinate of the vertex. So it would be 4, 5, and 5 is the one they wanted. They just wanted that coordinate, just the y. Then these problems 67 to 72 are graphing on a number line, and I thought that might mess with some people, so I thought I'd better do one of these. So 12 minus 2b is greater than, go ahead and distribute that 3b minus 9 minus 4. So 12 minus 2b is greater than 3b minus 13 by combining like terms. And then we would go ahead and add 2b to both sides. So 12 will be greater than 5b minus 13. Add 13 to both sides. And wait for the smartboard. There we go. So 25 is greater than 5b. Divide both sides by 5. And we will get this. 5 is greater than b. But to graph it, what we want to do is reverse the whole thing. So that will be b is less than 5. We always read from the side that has the variable. Now, at no point during this problem did I multiply or divide by a negative, and that would be when we would have to flip the sign. So what I need to do is just get some numbers on there that are around 5. And then remember that if there is no equals bar, it's an open dot, and I need the values that are less than 5. And I'm just going to label that number line as B right there to be precise about what's gone on with number 72. All right, that is it for this video.